So, good evening, everybody, ladies and gentlemen. Very pleased to welcome you here today to SLAC for our public lecture. Tonight I'm delighted to be able to introduce Professor Sarah Church from Stanford University, who's going to talk to us about whispers from the Big Bang. This seems to be a bit of a contradiction in terms, whispers and Big Bang, but Sarah's certainly the right person to talk to us about this. Sarah is a cosmologist. She got her first degree at Cambridge, her doctorate from Cambridge. This is not Cambridge, Massachusetts, but Cambridge in England. She has then since done postdoctoral work at the University of London, at Berkeley, at Caltech, and finally ended up here at Stanford. So if anybody is qualified to talk to us about what happened at the Big Bang and afterwards, it is certainly Sarah. Sarah also, interestingly, has just returned from Antarctica. I don't know if she was trying to get away from this heat, but she will certainly tell us about that, I hope, during her talk. So please, everybody, welcome Professor Sarah Church.
Well, thank you. It's certainly an honor to be here in this lecture series. Can everyone hear me? Can you hear me at the back? Yeah? Great. Okay. So I'm going to talk to you about a specific area of cosmology tonight. And cosmology is a large subject, and I only really have time to touch on a small part of it. But cosmology, to start with defining cosmology, it's the study of the origin and the evolution of the universe. And it turns out to I guess the field sort of started with that goal in mind, to understand how the universe got here. But it's become, in a lot of ways, a much richer field than that, because also we can explain how the objects in the universe came to exist, and in some ways we can actually explain why the universe behaves the way it does, and it's very exciting. So we believe the universe started with some event, which is colloquially known as the Big Bang. And the Big Bang started the universe off in a period of expansion, which continues today. Now, this is it's a very hard thing to represent the universe on a graph, and many people have made efforts. And this is a picture that I did not myself make, but is a picture that was made by NASA for one of their experiments, and it tries to sort of illustrate graphically what happened, which is that if you take a point in the universe and look at what happened to it through time, and time runs, I've had to use this scientific notation to indicate time, and what the numbers mean here is a 1 followed by the number of zeros that you show that are showed up here. So 10 to the 15 is a 1 followed by 15 zeros, and 10 to the minus 40 is 1 divided by a 1 followed by 40 zeros. So that's a very tiny period of time, an unimaginably small fraction of a second. And at the far end of the scale, we have the age of the universe today, which is about 13 billion years, which you can write as 10 to the 20 seconds. And so we believe the universe began expanding. It was very, very hot, and it was very, very small. So if you take 1 to be the size of the universe today, then it began, really there's nothing, there's no lower limit to how small the universe was when it began. It just, the smaller it was and the further back you look, the less we understand. So we think we're starting to have a framework for how the universe behaved when it had a size that was 10 to the minus 60 of what it is today. So a tiny, tiny fraction of the size of the universe that we can see today. And it started to expand, and this graph sort of illustrates how it expanded with time. And it started off by expanding extremely quickly, and I'm going to talk about that tonight. So it expanded by a huge number of times. And then the expansion kind of slowed down, and the universe cooled down, and this sort of colored mess here is just supposed to indicate things, I think, happening at the beginning of the universe, particle physics, all kinds of stuff going on. And then finally, galaxies formed out of the primordial soup of the universe. And just in case you're wondering, this thing at the end is the NASA satellite that this graphic was created for. The universe was created to be observed by this satellite at the end. But the interesting thing, the real kind of mystery really is that this experiment, along with others, measured the contents of the universe. And I'll talk about this in more detail. But the contents of the universe turn out to be quite different from the contents of this room, for example, or at least the contents of this room we can see. So you and I are made of atoms, and there are atoms in the table. There are atoms in us. The air that fills the room is made of atoms. But that turns out to be a very small fraction of the contents of the universe. And most of the universe is in two forms for which we only really have names. We don't understand too much about them. One of them is called cold dark matter, which is not matter, the kind of matter that you and I are made of. But 3/4 of the universe is made of something even more mysterious called dark energy. So this slide is intended to just give you a flavor of what it is I'm going to talk about, and I'll talk about these things now in more detail. So why is cosmology such a fascinating area of study? Okay, well, it clearly deals with a lot of very strange phenomena, as I showed you. But the thing that fascinates, so what fascinates me about cosmology, and I think what fascinates some of you about cosmology and why you're here today, is that it's the study of the past, but it's the study of the past in a way that's different from the way you study the past, say, for instance, if you're a geologist and you're looking at rocks, or if you're studying evolutionary biology and you're looking at fossils in rocks. The thing that's different about cosmology is that when we look out into the universe, we actually see the past. And the reason we can do that is because light travels fast, but it doesn't travel infinitely fast. So light travels at 300,000 kilometers a second, which is so fast that for the most part in our everyday lives we don't notice it. But when we look into the vast distances that span the distances between objects in the universe, this picture shows you galaxies, which are large assemblages of stars. It takes light a long time to travel between those objects. So for instance, light takes us 8 minutes. It takes 8 minutes to reach us from the sun. So if something happened to the sun, which it won't, but if it did, then it would take us 8 minutes to find out about it. Light takes 9 hours to reach us from the edges of the solar system. So we've launched various probes to study the planets over the last 30 years or so. And those probes are only just beginning to reach the outer edges of the solar system. They're actually a little bit further away than 9 hours. But the light still only takes about 9 hours or so to reach us from the most distant planets in the solar system. Light takes 4 years to reach us from the nearest stars. So it's obviously considerably further to the nearest star than it is to the most distant planet in the solar system. But that's still a tiny distance, because the most distant galaxies, some of which you can see in this picture, which is a picture from the Hubble Space Telescope, the small dots in this picture are all galaxies. And some of those galaxies are so far away that it's taken like 12 billion years to reach us. And the point about that, what's the point of that? Well, the point is that when you look at those tiny dots there, you're not seeing them as they are today. You're seeing them as they were 12 billion years ago. So to a large extent in this field, you don't have to speculate too much about what the universe looked like in the past. You can look and you can see. You can see what galaxies looked like 12 billion years ago, as long as you just make the assumption that this piece of the universe that you're looking at is the same as the piece of the universe we're living in. We see what the universe in our local area looks like today. We can see what it looked like in the past. And so that to me makes cosmology fascinating. We can actually see the past. So what do we see? What's the most distant thing we can see? So if I go back to this picture for a moment, we can obviously, as we look out, we see galaxies. Galaxies being very large assemblages of stars, hundreds of billions of stars. And as we look out, we see more and more distant galaxies. We see younger galaxies. But what do we see if we keep looking even further? And the furthest thing it turns out that we can see, which is the main subject of my talk tonight, is a faint uniform glow that fills the sky in microwaves. And by microwaves, I mean very similar waves to the kind of waves that operate your microwave oven. And what we're seeing is the remnant heat from the Big Bang. So the universe began as with this event that's known as the Big Bang. The universe was extremely hot and dense, and the microwave background is the remnant heat from that event. And it was discovered in 1964 by Penzias and Wilson, who later got the Nobel Prize for this discovery. And they discovered it not using an optical telescope. You would use an optical telescope to look at those galaxies, but a different kind of telescope that could detect radio waves, which is what microwaves are. And so they used this funny-looking telescope here in New Jersey. And what they found was when they looked in any direction in the sky, they saw this faint glow in microwaves. And that glow is shown here. This is a map of the sky. And if you turn up the contrast, so basically what you see is that this glow is uniform everywhere. Let me actually just skip forward a minute, because let me explain what that picture is. I'm going to show you a lot of maps tonight in which I'm showing the whole sky. So the whole sky that you can see if you plot what you see in every direction projected on a page. And just to give you a point of reference, if I took a map of the Earth and plotted it in the same kind of projection, it would look like this. Okay, it's just a way of projecting the sky, and you could just as easily use a projection that looked like this. You're familiar probably with different maps of the Earth. So this is a map of the sky in microwaves. So let me go back. So if you plot what the sky looks like in microwaves, you see this glow that's the same in every direction. But if you turn up the contrast in that picture, so imagine if you were looking at some very bright background, say on your television or something, some very bright picture, you could turn up the contrast and see more detail. You can do the same thing with the microwave sky, and what you find is sort of a random patchwork of spots on the sky. This is what's called a false color image, where the colors are used to indicate different intensities in microwaves. So the red parts are emitting more microwaves than the blue parts, okay? So I'll skip through that one. So the microwave background, as it's known, is actually brightest it's very bright in microwaves. It's also bright in what's called millimeter waves. But it's not visible at optical wavelengths. So if you took a regular telescope and you looked out, you see galaxies, and you see more and more distant galaxies with a larger and larger telescope. But you don't see the microwave background, because it turns out not to emit visible light. So light, microwaves, and millimeter waves are part of what's called the electromagnetic spectrum. They're all the same kind of phenomenon in physics. They're the result of electrons vibrating. And the electrons, the faster the electrons, the quicker the electrons vibrate, the higher the energy of the electromagnetic radiation that's emitted. So you can make a spectrum. We talk about the electromagnetic spectrum, which contains some familiar sounding terms. So gamma rays are extremely energetic, an extremely energetic type of radiation where the electrons are moving very quickly. And we go through to X-rays, the same kind of X-rays that are used to photograph your teeth or your bones. Ultraviolet radiation, which is, of course, well known because of its ability to change our skin, make it darker, that kind of thing. Visible light, of course, very familiar, from the blue to the red. Infrared, which is heat radiation. So if you put up your hand up to the sun, or you stand in the sun, the heat you feel is infrared radiation coming to you from the sun. And then less energetic electromagnetic radiation is in the radio and the microwave region. And the millimeter region is sort of between infrared and microwaves. And so this arrow indicates the range of electromagnetic radiation that you find in the microwave background. So you don't see the microwave background in the visible part of the spectrum. And at first, this might seem like a contradiction, all right? I've told you that the Big Bang the universe was very hot and very dense. There was this big explosion-like event that formed the universe. And yet I'm telling you that it's producing this sort of faint glow of radio waves that's so hard to detect. It was only discovered in the 60s, and it was discovered by accident. So it's not exactly, it's not drawing attention to itself in, say, the way the sun is. Okay, we didn't wait until the 60s to discover the sun. So how can that be if this incredibly energetic event produced this radiation? The reason is that the the microwave background is bright in millimeter and radio waves because of its temperature at the present time. And the fact is the microwave background is a lot colder today than it was when the universe formed. And I'm going to talk a bit about what I mean by that. So first of all, why would the temperature make any difference? Well, every object in the universe, including you and I, is emitting electromagnetic radiation by virtue of its temperature. So the fact that we have a temperature, so we have a temperature of about 30 Celsius, and what we're doing is we're emitting little packets of electromagnetic radiation, just based on the fact that we have a temperature. And every object in the universe does this. And the hotter the object is, the more energetic electromagnetic radiation it produces. And if you can make a picture. So if you were able to measure the little packets of electromagnetic radiation that you were emitting, okay, and you made a graph of how many packets were emitted at a given wavelength, it would look something like this. And every object in the universe emits radiation with what we call a spectrum that looks like this. There's some characteristic wavelength at which it emits most of its radiation, and then to either side of that characteristic wavelength, the amount of radiation that's emitted falls off. But this very characteristic shape enables you to measure the temperature of something. Now, something like the sun produces most of its radiation at visible wavelengths, and that's why we can see. Okay? We see things by reflected light. You and I produce electromagnetic radiation, but clearly we don't produce a lot of visible light. Okay? So if I turn the lights out, you wouldn't see anything. We're not all glowing in the dark. Okay? But if you had an infrared camera, you would see the people in this room quite clearly. Okay? That's what night vision goggles are. They detect infrared radiation, they detect heat instead of light. And so we're all busily emitting heat. We're a lot colder than the sun, so we're not emitting much visible light, but we're emitting a lot of heat. Okay? And so the type of radiation that a body emits tells you something about its temperature. All right? And the hotter something is, the shorter the wavelength of the radiation it emits. Now, if you make this picture for the cosmic microwave background, then what you find is the temperature is minus 270 Celsius. Okay, it's very, very cold. And that's why it took so long to be discovered. It's very cold, and it's not producing a vast amount of radiation. So again, why is it so cold? It's from the Big Bang, right? Well, what's happening is the universe is expanding. This was discovered by Edwin Hubble at the turn of the last century he was using a very large telescope, and he was looking at galaxies. And what he found was that every galaxy that he looked at, with the exception of a few that are in our local neighborhood, every galaxy was moving away from us. And the further away a galaxy was, the faster it was moving. In our local neighborhood, there's a relationship which says that the velocity of the galaxy is equal to the distance to the galaxy times a number called the Hubble constant. When you get further away, that relationship gets more complicated. But for the most part, in nearby universe, you can use this relationship. And that was the first evidence for the expansion of the universe. The implication of this result was that at some point everything in the universe was a lot closer together, and this event, the Big Bang, started everything expanding, and so over time everything is getting further away. Now, why does that make the microwave background cold? Oh, well, before I do that, let me explain how Hubble did this measurement, because that's important. How do we know this? The reason we know this is if you take the light from the sun, remember I told you that the sun emits mostly visible light. If you take that light and you shine it through a prism, you can break the light from the sun into its constituent colors. You've probably all seen this through pieces of glass, reflections from glass or from mirrors. It breaks the light into colors. This is a picture that shows the light from the sun. And what's happened? So each of these bars across here is a color from the sun. And what's happened is they've just chopped the picture up so you can get the whole thing on one page. Okay, so instead of having this very long picture that goes from red to blue, they've just chopped it up and put it on a single page. And this is actually a real picture of light from the sun. And so if you were able to magnify greatly the spectrum that you get, say, from a prism, you would see the same thing. What you see is the light you have a spectrum from red to blue, but at various points you see these dark lines. And this is real, okay? This is not some error in the measurement that was made. These lines are real. And each of those lines is called a spectral line. And that line is telling you something about the elements that are contained in the sun. So the sun is mostly a big ball of hydrogen. It's got some helium in it, and it's got some heavier elements. It's got lithium and beryllium and sort of the whole spectrum of elements in it. And each of those elements will absorb a specific wavelength of radiation. And so that's what these dark lines are. They're telling you about the elements in the sun. And you can then make comparisons in the laboratory. You can look at elements in the laboratory, and you can generate these lines. And so you can identify these elements in the sun. And in fact, the element helium was discovered in the sun by looking at spectral lines that didn't seem to have any equivalent on Earth. It was actually discovered in the sun before it was discovered on the Earth. Now, the connection to cosmology is the following. That if you look at the spectral lines in an object that's moving, what happens is the spectral line changes wavelength. So the wavelength is the distance, the distance either between two troughs in the wavelength of the radiation or between two peaks. It's the characteristic length of these oscillations. And so if you have an object that's at rest, okay, so say our galaxy, a star in our galaxy, that's not moving very quickly, there will be some characteristic wavelength to each of the spectral lines in the light from that star. Now, if you then send this object moving, if this object then starts to move, what happens is the wavelengths get stretched out, and that's an effect known as Doppler shift, and it happens with all types of waves. And the place you've probably most frequently come across it in your everyday life is if, let's say, a fire truck is coming towards you and its siren's going, and you may have noticed that it comes towards you and the pitch of the sound changes, so it sort of goes, meow, it changes as it goes by, okay? And that's the same thing. That's Doppler shifting. It's the changing of the wavelength of the sound waves. And light waves do the same thing. It's just that you have to be moving extremely quickly to make a change. So if I go and run to the other end of the room, I won't change color. Okay, you have to go very fast. All right? And the only things that are really going fast enough to be able to tell this are astronomical objects that are traveling at very high speeds due to this expansion of the universe. And I promise there won't be, this is actually the only math in my talk tonight, okay? But this is how we characterize the speed at which these objects are traveling. Because of this well-defined relationship between the speed that a galaxy is traveling at and its distance, we can refer to distances by something called the redshift, which is the change in the wavelength. So I use this funny symbol lambda to indicate wavelength. It's the change in the wavelength divided by what its wavelength should have been if it was at rest. And that thing is called the redshift. Now, you don't have to remember that. All you have to remember is that larger redshifts means that an object is further away. And therefore, by implication, because of the expansion of the universe, it's traveling more quickly. So when I say redshift, I'm talking about distance. So something that's at a redshift of 1 is closer to us than something at a redshift of 10. Okay, so just think of it as a unit of distance. And the reason it's called redshift is because things that are moving away from us emit light and other forms of electromagnetic radiation that are redder than they have longer wavelengths than they would if the object was stationary. And so the upshot of the expansion of the universe, there's nothing very, there's nothing too complicated about understanding why things that are further away are traveling faster. Okay, there's not actually very deep physics in that. Just think about if this room were suddenly to get bigger for some reason. Okay, it was just to increase in size, which is very unlikely, but it's a good example. Say that picture on the wall would actually be traveling faster, traveling more quickly away from me than this chair would be. Okay, so if everything's expanding at a uniform rate. Okay, and that's all that's happening when the universe is expanding, it's just physically getting bigger. And so things that are further away appear to be moving more quickly. So the expansion of the universe causes more distant objects to recede at higher speeds, okay? All right, so that's a very long explanation about why the microwave background is cold. Remember, the microwave background, when you look at the microwave background, what you're looking at is you're looking further and further out in space, and then finally you look so far back that you can almost see to the Big Bang. Almost, not quite. And that what you're seeing then is the microwave background. It's very far away. It has a very large redshift, so it has a redshift of 1,100. So it's very much further away than something with a redshift of 1. And so it's traveling very quickly, okay? And so that means it's very, very redshifted. So if I go back to my picture of the black body spectrum, remember there's this characteristic wavelength. And that characteristic wavelength, as an object moves more quickly, the redshifting causes that to move in this direction, and the object appears to be colder. So that's why the microwave background appears cold, even though the event that formed it was very, very energetic, very hot event, the Big Bang. It was the earliest moments of the universe. So what are we looking at? So let me try and illustrate this in a different way. So here we are. So what you can do is you can think of us that we're not at the center of the expansion. Okay, that's a very common, well, not a common misconception, but it's a common source of confusion, because I've told you that every galaxy appears to be moving away from us. So the usual question is, does that mean we're at the center of the universe? Well, no, it doesn't. It's simply a perspective effect. So we're in something that's getting bigger. A good way, there are many, many analogies. I'll use a couple of different ones tonight. But one of the good analogies you can think about the expanding universe is a cake, a baking cake, okay? A raisin cake, let's say. So you have this mixture, and it's full of raisins, and you stick it in the oven, and it starts to rise, okay? Now the cake tin will actually stop it expanding in every direction, but pretend it's just a blob, okay, of cake. And it will get larger, okay? And all the raisins are moving because the cake is carrying them along. And every raisin will think that every other raisin is moving away from it, okay? Because the cake's getting bigger and they're all getting further apart. And provided they can't see the edges of the tin, they'll have no way of knowing where the center of the cake is. And we're in that situation. We think that it looks from our perspective as if we're at the center of the expansion, but that's just a perspective effect. We're just in something that's getting larger. So here we are. And in every direction you look out, you look back in time, okay? So I've labeled this look back time. So if you draw an arrow in any direction, you look further back in time. And therefore, by implication, you look out further in redshift, okay? So something in our immediate neighborhood, so say the sun, has a redshift of 0, okay? It's very, very close to us. But so if you look out as far as a redshift of 6, everything you see between us and a redshift of 6 is galaxies. You see a lot of galaxies, okay, all at different distances. And then if you look further out, you actually don't see anything. You see very little at all. And that's because we're looking so far back that galaxies haven't had time to form. We're looking back in time. So what we're seeing is a soup of gas that hasn't yet had time to form into stars and galaxies. And then you look further out still, you're looking earlier and earlier in the universe, and then suddenly you can't see any further. And the reason is that the early universe was considerably hotter than it was today. So the universe started off extremely hot, and it was so hot that the primordial gas, which was mostly hydrogen, was separated into its constituent particles. So it was a big sea of protons and electrons, which is a very similar state to what you find in something like the sun. So you can't see through the sun. Okay, the sun you can look at the surface of the sun, you see the surface of the sun, but you can't see through it to the other side. Same with a candle flame. You have the same kind of thing going on there. You have gas that's what we say ionized, and you can't see through ionized gas. So in every direction you look out and you wind up. You can't see any further. And that's because you're simply looking so far back that the universe is hot enough to have ionized the gas, and it becomes opaque. And that's what you see, that's where the microwave background is coming from. It's it's heat basically being emitted by the ionized universe, and it's getting redshifted because it's very far away, and so the expanding universe is making it, is redshifting it, so it appears very, very cold, even though it's coming from a time when the universe was very hot. And if you look back further still, you've got, it's completely opaque here. You can't see any further. Now, I know this is a complicated diagram, but if I was to give you one, if I wanted to give you one take-home message from this picture, it would be that we don't know how big the universe is, all right? Because we can only see a certain part of it. In every direction, as we look out, we look further back in time, and we can only see so far. We can only see to the point at which the universe was so hot that it was ionized gas, and you can't see any further. So there's no way to know how big the universe is. So the universe, we say the universe is infinite. We just have no way of knowing. There's no reason why it shouldn't be infinite. You get to say those things very glibly after you've been a cosmologist for, you don't really think about it anymore. And then you suddenly hear yourself and like, my goodness. No, but anyway. So let me get back to the microwave background, which is, after all, the purpose of my talk. So the title of the talk is Whispers in the Big Bang. Okay, so it's a whisper. The microwave background is the relic of this incredibly violent event, but time and distance, if you like, have weakened it. So it's this very, very faint glow. It's not really hard to measure. Penzias and Wilson actually discovered it by accident. And since then, it's been mapped by many, many different experiments. You can detect it with a carefully built experiment. But if you build a really careful experiment, this is actually the result of a satellite, this NASA satellite that was launched. You can measure very small variations in the amount of microwaves that are being produced at any point. And so what you're measuring is you're measuring very small differences in the spectrum from these different points. And what it tells you is that the temperature of the microwave background is not completely uniform. It's not uniform in every direction, but it doesn't vary by very much. So this red patch is slightly hotter than the blue patch, and the differences in temperature are only a few parts in 100,000. It's a very, very tiny difference in temperature. Now, what is this? Why is there this structure? Well, what it's telling you is telling you that the Big Bang was not, that the universe, when the universe began with the Big Bang, it was not a completely uniform thing. Right? The Big Bang had a little lumpiness in it. And that's good, because it was those lumps that eventually made the structure that we see today. So we have these temperature variations, okay, the level of a few parts in 100,000. And what they're telling us is that there are these bits, these parts of the universe, the red parts, are a little bit more dense than the blue parts. There was a little bit more, the gas was a little bit more concentrated there in the early universe. And so what would happen if you stared at the microwave background for a very long time? You'd see it very slowly shift. And the reason is that because, remember, you're looking out into space and you're looking back in time. And the older the universe gets, the further you can see. Okay, lights have more time to travel. The universe has cooled down a bit. These little spots in the microwave background would form into stars, early stars, and then those stars will form into clusters of stars, which are galaxies. These tiny patches are indicative of small variations in the density of the universe that eventually form the structure that we see today. So they're extremely important. This is not, it's a tiny fuzz, if you like, in the temperature of the universe, but that tiny, tiny variation makes everything that we can see today. It's very, very important. So the standard cosmological model, so-called, and believe me, there have been a lot of different standard cosmological models over the year, and every time it changes, they call it the standard cosmological model again. So, but the standard cosmological model says that there was this lumpy, hot, dense Big Bang. So the lumpiness were these small temperature variations. And so in the Big Bang, you have there's fundamental particles undergoing interactions at very high energies, which is physics code for temperatures, very, very high temperatures in the early universe. And finally, it cools enough so we can actually see something, which is the microwave background. The universe expands and cools, and these small density variations form galaxies. Okay, so that's the model, and the details. The overview of that model hasn't changed a lot since the cosmic microwave background was discovered. What changes over the years is how well that model works and what has to be added to it to make it work. So the original model, which was formulated very soon after the microwave background was discovered in the 60s, said the following. There were just a few important quantities. You could think of them as sort of ingredients for the universe. Okay, so if you're making the universe, what would you need? Well, you need stuff in the universe. Okay, so the universe has some mean density. And that's important because it's matter that causes gravity. Okay, so the reason I'm stuck to the Earth and I don't just float around is because the mass of the Earth is creating a gravitational pull that holds me to the Earth. And in the same way, every object in the universe exerts a gravitational pull on every other object in the universe. So if you think of the Big Bang as being this event that started the universe expanding, all of the stuff in the universe exerts a gravitational pull on the rest of the stuff in the universe, and it slows the expansion rate down. So you can think of it, it's not quite right, but you can think of it like a big explosion, and it kind of slows down over time. The Hubble constant, which is this number that Hubble measured, which told you how fast an object was moving compared to its distance, the relationship between the distance to an object and its velocity is a measure of the expansion rate at a given time. Okay? So in principle, if you know the density now, and you know the Hubble constant, and if the only thing acting on stuff in the universe is gravity, you can predict exactly what the universe looked like in terms of its size and expansion rate at a given time. The combination of those two quantities controls the expansion of the universe. So that's a recipe for what the universe looks like with just two ingredients. And then there's a third thing that you need to explain what we see, which is you have to have these initial variations in the density as a function of position in the universe that makes stars and galaxies. So that was a very simple model. But as soon as people started to think about it and to test it, they found a couple of problems that were not, that sort of vexed people's minds, but didn't mean that the model was wrong. It just meant that something had to be added. So the first question is actually a question that doesn't always occur to a lot of people who actually work in the field, but it's actually a very fundamental question. What caused the universe to expand? And the reason I think we don't think about that question too often is a lot of us, when we're introduced to the idea of the Big Bang, especially if you in popular literature and that kind of thing, it always sounds like an explosion, okay? But nobody then really asks the question, well, you know, what caused it? What was the event? Why does the universe expand? Okay, with an explosion, you've got a generation of chemical energy, and the chemical energy heats up the air, and the air expands and pushes everything apart. Okay, so what's the equivalent for the universe? That's clearly not what's going on in the universe. So that was one question. And then the second question is a little bit more subtle, but was actually quite important, which is that I've been showing you this picture of the microwave background, and I've told you that it's uniform. So its temperature only varies to a few parts in 100,000. But that's actually quite mysterious, okay? And the reason is that there's no reason. The universe that we see is so vast. There's no actual reason why you would expect the temperature to be so similar in every place, right? There are these small variations that are due to the change in density, but the temperature is basically the same over here as it is over here. So why is that mysterious? Well, let me try and give you an example, okay? So it's pretty warm in here tonight, right? So somebody opened the door, and the door to the outside was open. A stream of cool air would come in and cool the room down, but it would take time for that air to travel, that cooler air to travel all the way down to me. And so I wouldn't get cooler immediately. There would be some time while the room reached a new temperature. And the same thing's true of the universe. You start the universe off with this event, and there's no reason why the energy of that event should have been the same everywhere. And so it would take some time for the universe to settle to a uniform temperature. And there just hasn't actually been time for the universe to acquire the same temperature if all that's going on is that we have a universe that's expanding and gravity is slowing down the expansion. You actually just can't do it. It's a problem. So it's a subtle problem, but it's nonetheless a problem. And then just in the last 10 years or so, an even more troubling problem arose, which is that if you if you calculate the expansion rate of the universe as a function of time, just based on the fact that there was some energy input that started the universe expanding, that's characterized by the Hubble constant, and then gravity slows the expansion down, you should see the expansion rate slowing over time. And you can measure the expansion rate at different times by using this Doppler effect. You measure the velocity, the speed at which a galaxy is receding, and then you can measure the distance to the galaxy. Now distance measurement actually turns out to be hard, but one way to do it, which some of you may have heard of, is that there are certain stars, when they reach the end of their lives, explode in extremely massive explosions that can outshine their galaxies. So this is a picture of a galaxy, and this is a single star in that galaxy that has exploded. And it actually looks like that star has no connection with the galaxy, and that's because it's in the outer reaches of the galaxy, and it's so bright, it hugely outshines the rest of the galaxy. And you can use these supernovae as light bulbs, and you can assume with some accuracy that they all have the same brightness, and so you can use them as a means to measure distance. And so if you do that, if you measure the expansion rate of the universe by using the supernovae to measure the distance and the redshift to measure the speed, you find that the expansion rate today is faster than it should be, and that's a problem. Now, physicists are inventive people, and so they very quickly came up with a way to at least characterize this extra expansion. Now, so physicists, I'll tell you a secret, okay? Physicists are very good at giving names to things, which makes it sound like we understand them, all right? But they're just names. At least at the moment, it's just a name. So people came up with this idea of dark energy. And dark energy is an unknown repulsive force that is accelerating the expansion of the universe, okay? So it's another name for the problem, all right? So how does it work? Okay, so let's say you've got two objects in the universe, and gravity is pulling them together. So gravity should slow down the expansion of the universe. What dark energy is doing, dark energy is making the universe bigger. So these objects they have a position in the universe, but the universe is getting bigger around them, and so they're getting further apart. All right? Now, the weird thing about dark energy compared to gravity is that when these two objects get further apart, they get further apart because the universe is expanding. Gravity gets weaker because they're further apart, and that's what gravity does. It's strong when two objects are close together. It's weak when they're further apart. But dark energy is just something that's making the universe bigger, and it doesn't get weaker with time in the same way. So over time, dark energy starts to dominate the expansion of the universe compared to gravity. And so the expansion rate does not appear to be what it should be if there was only matter in the universe. And that's why we have this notion of the contents of the universe being just a tiny bit of ordinary matter, like you and I are made of, then a large section of this cold dark matter, which unfortunately I don't have any time to talk about tonight. So afterwards there's going to be a session where you can ask questions of people outside, and so ask about dark matter then. And then dark energy, okay? All right, so what is dark energy and where does it come from? Well, I can ask the question. I can't give you the answer. But I can give you a possible answer, okay? So dark energy is probably related to something else equally mysterious that we think happened in the early universe called inflation. So there was a process called inflation in the early universe. And inflation is probably connected to dark energy because imagine you had a very large amount of dark energy in the early universe. So dark energy is something that makes the universe bigger, okay? And so the more of it there is, the faster the universe gets bigger. So if in the very early universe you had a huge amount of this stuff called dark energy, or dark energy-like stuff, the universe gets bigger very, very quickly, okay? Now, the theory of inflation actually was formulated before before dark energy the effects of dark energy were discovered, and so it's probably telling us that these theories are not too far from the truth because something else has been discovered, namely dark energy, which you can explain in a similar kind of way. But inflation is a wonderfully exotic theory because it says that the universe underwent extreme expansion for an unimaginably brief moment. So in fact, here's how brief this moment is, okay? That many seconds, right, which I think, if I remember rightly, I think that's 34 zeros. You can count them if you want while I talk about the rest of the slide. But what happened in that moment was, if you were looking, so imagine if you were outside, okay, and you looked, you just concentrated on one small piece of the universe. You looked at that piece of the universe, and it was this big, okay, as big as that dot on the screen. In that length of time, that piece of the universe would expand to the size of the present-day universe. Boom, there it is, okay? And then it kept going, all right, because there was dark energy, and it was making the universe get bigger, okay? So it's sort of an interesting philosophical idea that actually, if inflation is right, the universe kind of sprang into being, okay, which is sort of an interesting philosophical thing if you think about it. So what people are trying to do is they're trying to explain that with physics, the physics being the theory of inflation. And then inflation ended, so this could have just gone on forever, right? Because I said that dark energy doesn't get any weaker as the universe expands. And that would be a problem, okay? So if inflation just went on forever, nothing interesting would ever happen. But for some reason, inflation ended because a very large amount of this dark energy was converted to matter and the microwave background, okay? Now, conversion of energy between different forms of energy and matter is not, there's nothing too exotic about that. That's something that happens in other areas of particle physics. But fortunately, enough of the dark energy was converted to matter that the expansion thankfully slowed down enough for stuff to be formed. Well, this is a nice theory, a very nice theory. It's been around since the 80s, and it solves many problems associated with the model, okay? So this somewhat fanciful picture shows you what's going on. You have this big question mark, the dawn of time. You have this tiny fraction of a second when inflation happens, and then the universe becomes sufficiently transparent to see the microwave background when the universe is about 400,000 years old, 380,000 years old. And then 3.7 billion years later, you have us sitting here today, okay? And inflation explains why the universe expands at all. The reason the universe expands, the reason the universe is expanding today is because, boom, there was this process of inflation, this dark energy-like stuff that started the universe expanding. It explains why the temperature is uniform, because you're only looking at this tiny piece of the original universe. Remember that little dot suddenly went boom and became the size of the existing universe. So that little dot had plenty of time to reach the same temperature, okay? It explains the origin of structure, and I don't have time to talk about this at all, but basically this lumpiness is due to quantum fluctuations that can be expanded to enormous size by the inflation process. And possibly it can explain the existence of dark energy because there's almost certainly similarities in the mechanism, okay? So it's a great theory, it explains lots of stuff. And the details can be tested with observation, in particular the microwave background. So how do you test that? Well, an important test is to measure the geometry of the universe. So let me talk about geometry, then I'll explain what I mean by the geometry of the universe. So these pictures show you examples of curved two-dimensional spaces. So if you take a piece of, well, if you take a flat sheet and you deform it, it's actually very hard to take a flat piece of paper and make these shapes with it. But you have to cut pieces out and stick them together and that kind of thing. But you can create these surfaces that are curved, okay? Here's a flat piece of paper. And the red triangle is the way that you can measure the curvature. So the angles of a triangle on a flat surface add up to 180 degrees. If your surface is negatively curved, the angles of that triangle add up to less than 180 degrees. And if it's positively curved, they add up to more than 180 degrees. So these are curved two-dimensional spaces. And the universe can also be curved. So Einstein came up with a theory of gravity, which is called general relativity, and that allows for the universe to be curved. And the amount of curvature is determined by the presence of matter and energy. So if you have a large mass and you look at the path of a light ray, far from the mass, space is flat and light follows a straight path. Close to the mass, the light ray gets curved. Okay? And the reason is that space is curved and light will follow the lines of the curvature. And this has been seen. This is a picture of a cluster of galaxies, which represents a very large concentration of mass. And these arcs here are curved, are bent light from galaxies that are behind this cluster of galaxies. So this is a theory that, again, creates phenomena that are not something you encounter in everyday life, but they are seen in astronomy. They're real. And so the matter in the universe, both matter and energy, curve space. But inflation predicts that the universe should be flat. Now, why does inflation predict that the universe should be flat? It's the same reason that the temperature should be the same everywhere, that we're only looking at a very, very tiny piece of the universe. So as an analogy, imagine I wanted to try to measure the curvature of the Earth. Okay, well, I've just showed you that one way to measure curvature is to draw a triangle, so of the flat surface, of the two-dimensional surface of the Earth. A way to do it is to draw a triangle. And you can measure the angles inside the triangle, okay? Now, imagine that the only area on the Earth that was available to you to measure whether the Earth was curved or not was this room, okay, the floor of this room. Well, you can make your triangle, but chances are it'll turn out to be, it'll turn out to tell you that the surface of the Earth looks pretty flat if you just use this room, okay? So if I walk from this side to the other, I'm not going to tilt over with the curvature of the Earth, right? The same thing's true of the universe. We only see a little bit, okay? So what inflation did was it expanded the universe, and here's just a graphic sort of showing what's going on. This is another analogy where you can think of the universe as being the surface of a balloon, an expanding balloon. And so what we're looking at, we can only see a very, very tiny part of the surface of this, the two-dimensional surface of this three-dimensional sphere. So you extend the analogy and think about the universe as being the three-dimensional surface of a four-dimensional object. But you only see a little bit of it. So if you measure the curvature, the universe looks flat. Inflation tells you that it has to be true. It doesn't matter what the initial curvature is. Today it looks flat. So how do you measure that? Well, you can measure the curvature using the microwave background. And the reason, so if you look at this map of the microwave background, you can see that there are patches that are very red and patches that are very blue. And what that's telling you is that the temperature is different. But you can see that these patches all seem to have a characteristic size, okay? There's not a big red patch that's this big, and there's not a big red patch that's very, very tiny. And it turns out that you can predict the actual physical size of these things from the physics of an ionized plasma, which is what the universe is when it's young, okay? And I'm not going to go into the details of that at all. Suffice to say that we know how big these brightest patches are. And then if space is curved, the light rays from that object will follow either straight lines if the universe is flat, or curved lines if the universe has positive or negative curvature. So curved space acts as a lens, either magnifying or demagnifying the object. And so you can look at the characteristic sizes. So I expanded a small patch of this map, and so they would be larger if the universe were positively curved. They would be smaller if the universe was negatively curved. And what it turns out is that they're exactly the right size for the universe to be flat, which is what the prediction of inflation is. And due to the fact that I'm running out of time, I'm not going to talk too much about that, except to say that the universe is flat. But what caused inflation? Well, that's a question for another day. It's not completely known yet. There are a lot of people working very hard to understand why that is. Not me, let me hasten to add. I'm an experimentalist and I just measure things. But there are people working hard to explain inflation, and it can arise in exotic theories of particle physics at energies that are far beyond those that are testable in ground-based accelerators. And any good theory must be testable. And you can actually test inflation by looking, again, at the microwave background. And what you can do, I think I have a couple of minutes to explain this, is you look at what's called the polarization. So an electromagnetic wave is made by a vibration of an electron. It creates a vibration in something called an electric field. And there are two directions that the electric field can take. You can decompose any wave into these two directions, which I show by showing the electric field vibrating up or down, or in and out of the board. And that's how, so how many of you have Polaroid sunglasses, right? A lot of you probably do. So you know when you look through a Polaroid sunglass, the world gets dimmer. And that's because you're cutting out half of these waves. So here's a schematic that shows you how Polaroid sunglasses work. If the electric field is vibrating in and out of the board, it gets cut off by the Polaroid, because the Polaroid only lets through things that are going up and down. So the world gets dimmer. And in fact, if you're looking at something that's completely polarized, so the electric field is just in one direction, you won't see anything at all. Okay? But because On average, light is equally polarized in both directions. If you put on your Polaroid sunglasses, everything just gets a bit darker. And the same thing's true of the microwave background. So again, I will skip the details. All right, I'm skipping a lot of details. So let me finish up by telling you how we actually measure the microwave background, which might be of interest. So we actually measure the microwave background by making cameras. Okay, now this is actually designed to measure the polarization, and like I said, I don't have time, unfortunately, to talk about the details. But we make these cameras. This camera is about this big. Okay, it's a very at these wavelengths. It's very difficult to make large cameras. So you probably all have megapixel digital cameras sitting at home. Okay, we don't make megapixel cameras yet. Okay, partly because they'd be really big. So this is a 31 pixel camera, and it's this big. Okay, so a megapixel camera can't do it. But what we do is we take this camera and we put it on a telescope. This is actually a telescope. It's a very funny looking telescope. It looks a bit like it's a satellite, like a satellite dish. So there's a dish in there, and there's a little mirror up here that reflects the light down to our camera. And then this is foam that supports the mirror. Okay? And this is at the South Pole. So you heard that I went to the South Pole. And this is not me, actually. This is a very intrepid person who's actually down there right now, because it's winter down at the South Pole, and he's down there running our experiment. So this is how you measure the microwave background. You can also do it from space, but the point is you need to be somewhere that's very, very dry. How do you get to the South Pole? Well, it's very difficult, actually. You can only go there from mid-November to mid-February, and during the winter, no one can get in or out, so you pay someone a significant incentive to stay down there and to agree to be in the dark for 6 months. But if you want to get down there, this is actually me. You get on one plane, you fly to New Zealand. You get on a second plane, you fly to the pole. It's very, you sort of trudge around in these funny clothes, and if you're working outside, it's horrible. And so this is actually someone covered with a quilt trying to work on the telescope. It's very, very cold. Not me. I was inside in the warm. Someone else took that picture. So why the South Pole? Well, so we're looking in this part of the spectrum, and you and I emit copious amounts of microwaves and millimeter wavelengths, and so our telescope is emitting huge amounts of microwaves. That's bad, okay, but at least it does it in a sort of a uniform way, and you can subtract it. So I've got a little cartoon here that shows what's going on. Here's what we're trying to measure. Here's what the telescope does. It washes everything out, okay, but you make a very careful measurement, and you can turn up the contrast, okay? But you can't do it I couldn't do it from outside on the grass here. The reason is the atmosphere. The atmosphere emits huge amounts of microwaves, and worse, because of the water in the atmosphere, those microwaves vary with time. And so it'd be like trying to measure something, it'd be like trying to make those beautiful pictures that the Hubble Space Telescope makes through the haze that's covered the Bay Area today. So you go to the South Pole, where the water's all frozen, okay? So anyway, I don't have any results from that experiment. I just wanted to show you quickly how the experiments are made, because otherwise it seems very abstract. But the next few years, that should say years there, we'll see results from QUAD and the next generation of experiments. QUAD is our experiment. And NASA is planning a satellite. There's going to be a new satellite to follow up on the old satellite, but probably not for a few years yet. So let me conclude. The microwave background is a relic of the early universe, which we call the whisper of the Big Bang. The small temperature variations provide strong evidence for inflation. Future measurements will test the physics that causes inflation, and we will learn things about physics. So that could be my conclusions, but I always like to end these kinds of lectures with a word of caution. I think this is a good theory, that our large-scale picture of the universe works, and the agreement between theory and data is excellent. But the details are poorly understood. There should be many more public lectures in the future as we try to unravel the details of this theory. What is dark matter? I didn't talk about dark matter at all, but its origins are starting to be understood, but it's still fairly mysterious. What is dark energy? These are not trivial questions. 96% of the universe is in a form that is not you and I, okay? And we don't understand the details. So I always like to end just by pointing out that, it's easy for us to stand up and say, here's a name for things, here's a theory, but we still have to understand it. There's a lot of work to do. But anyway, thank you for letting me tell you some of the details, and I will end on that note. So I think I can take a couple of questions, but then we'll do most of the questions outside, right? So I'll take like 2 or 3 questions. Yeah, in the middle there.
It looks to me that you have in a diagram saying that where was the edge that we can see of the universe. You had a redshift number there.
Yeah,
You also mentioned that that was where we could see cosmic background radiation. And I was wondering if you measure redshift of cosmic background radiation, how can we tell what is it made from?
yeah, that's a good question, because actually we don't really measure the redshift of the cosmic microwave background at all in the sense of measuring spectral lines. What's done is to measure the temperature of the microwave background today, and then we say, okay, well, we know we can't see any further than the point when the universe is a certain temperature, and we know how the temperature of the universe changes over time. And so you can figure back to what age the universe was when the microwave background was emitted, and so then you associate a redshift with that. But yes, you actually don't measure the redshift of the cosmic microwave background using the spectral lines. So you can't sort of tell what it's made from in that sense. What's been done is you assume that you have this theory which tells you that there's this primordial gas and it was all hydrogen, and the universe was hot enough actually for fusion to take place in much the same way that it takes place in the sun, and it forms elements. So fusion is a process by which hydrogen nuclei are fused together to make heavier elements, helium, lithium, so on. And you can calculate the proportions of these elements, and then you can measure them in stars, and they turn out to be in good agreement. So I've only told you a tiny piece of the theory tonight. There's a huge network of observations that have to coincide and agree for this to work. So I think over there. Yeah.
The speed of this inflation exceeds the speed of light, if I understand you correctly.
Right. It's that's something that seems strange. I agree. It's not so. It's actually what's actually happening is the best way to kind of explain it. Is the universe is just getting bigger, okay? And there's actually no barrier in Einstein's theory to that happening at those speeds, okay? What Einstein's theory tells you is that you can't have a transfer of information faster than the speed of light, and that's not violated at any point in the theory. But the universe getting bigger at that speed is actually allowed by Einstein's theory of general relativity, so there's no contradiction there. But it does, I agree, contradict this statement that we always make that nothing can exceed the speed of light. I think I'll take a question from over here, and then I should probably, we will take all questions. We will try and answer everyone's questions outside, but I'll take this one here.
I've read that future experiments to measure cosmic microwave background are going to try to discover primordial gravity waves.
Right.
What are they, and how would you discover such a thing?
So let me assure the audience that this is not a plant, okay? But I do actually. Oh, the question is, so why are we measuring polarization? We're trying to measure gravity. We're trying to look for gravity waves, okay? And they turn out to change the polarization of the microwave background. And the question was, what are gravitational? That was your question, right? What are they? So gravitational waves are something that's allowed by Einstein's theory. And what Einstein said is that gravity is caused by mass and energy, and his theory was able to explain the geometry of the universe. So there's a deep relationship between geometry and mass, and what his theory also allows for are variations in the strength of gravity that can travel through space in a wave-like motion. And what a gravitational wave does is if you put a ring, let's say you had a ring of particles, they could be things orbiting the Earth, satellites orbiting the Earth or something. And if a gravitational wave went by, what it would do is distort that ring, okay? And so the satellites would sort of move. They'd be like floating floating buoys or something on the surface of the ocean, the wave goes by and they go up and down as the wave goes by. And that's the same, that's basically what gravitational waves are. They're propagating disturbances in the gravitational field. What's much harder to explain is why that changes the polarization of the microwave background, but it does, and it changes it in a way that you can distinguish, and that can tell you about the gravitational waves. And what inflation, the theory of inflation produces these density fluctuations that make us, but also it can produce these disturbances in the gravitational field that are gravitational waves, and that's what we're trying to look for. The effect is extremely faint. So that's why the next satellite will be looking for these gravitational waves, but probably won't be launched for at least 10 years, because we have to figure out how to make such a very, very sensitive measurement of the microwave background. So I should probably stop at this point, but encourage people to hang around and ask questions outside. But it'll be me and a group of other people too. So thank you for your attention.